Hello everyone, welcome to Skill Dev. Trey here, and in this lesson, we're going to solve valid Sudoku board. This prompt states to write a function that returns a boolean indicating if a Sudoku board is valid or not. And note that we only care if the board is valid. We are not concerned if it's mathematically solvable. So we'll look exactly at what valid means. But with a normal Sudoku board, valid means you can't have the same number in any column, row, or subsquare. So you're just given an initial board and you want to know if this initial board is valid. It may or may not be actually able to be solved based on the construction. It's just simply checking for the validity of this initial state. So the constraints for this question are that it should work for any K by K board, not just the standard 9 by 9 board. So this board can take any size. The board must be square, so the rows and the columns must match at K by K. And it will be composed of J by J subsquares. So a standard Sudoku board is K by K 9 by 9, and the subsquares are 3 by 3. Then inside any row, column, or subsquare, you can only have the numbers 1 through K appear once. If they appear more than once in any of these, it will be invalid. So with a normal board, 1 through K is 1 through 9. So those were a lot of different variables to take in. Let's now visualize what they all mean and how they relate to a valid Sudoku board. So the length of each side is K. So we're calling a Sudoku board a K by K board, and a Sudoku board must be square, so all the sides will have the same length. If a Sudoku board is not square, we know it can't be valid. We're calling J the length of the sides for the subsquare. So J is the square root of K. So since the sides are J by J, it will contain K items. So in a standard Sudoku board, the length of the sides are 9, so K is 9. A subsquare is going to contain 9 items, and it's going to be 3 by 3 for the sides. So a valid Sudoku board is one large square, and then is composed of K smaller subsquares. So there are 9 subsquares in a standard Sudoku board. So not only does the board have to be square, but it must also be able to be composed of these K subsquares. So a 10 by 10 board would be a square, where K is 10, but it would not be a valid Sudoku board because the square root of 10 would not be a whole number and could therefore not create these subsquares. So the next K that would be valid is 16. So you take the square root of that, and you would have subsquares that are 4 by 4 in their side lengths, and there would be 16 total. So there would be 4 subsquares along the top, down the side, making 16 in total. So to reiterate, for a board to be valid, it's all about this larger square that is composed of subsquares. So the square root of K must be a whole number to be able to create the square and subsquares. And then finally, we're calling N the number of items in the Sudoku board. So that's K by K. So in the standard Sudoku board, where the side length is 9, we have 81 total cells. And now let's look at some examples. We're going to have the numbers 1 through K in a Sudoku board, but a number of 0 indicates that a cell is empty. So this first board is a standard 9 by 9 board. There are no duplicates in a row, column, or subsquare. So we return true. With this example, there are no duplicates in a row or subsquare, but the shape is not valid. It's not a square, and it can't be composed of those subsquares. So we return false. In this example, it is a valid shape, 4 by 4, where the subsquares are 2 by 2. So we have 4 total subsquares in the board. But in this last column, we see the number 4 appears twice. So we return false. So in those examples, we saw there are two ways for the board to be invalid. The first is the shape. The board itself is not square, or it's not able to form those subsquares. And the other way it can be invalid is the number placement, if we find a duplicate value in a row, column, or subsquare. So we see we can check for a valid shape just by using simple mathematical operations. The input is a matrix, so we just need to check that the number of rows and the number of columns are equal, making this outer shape a square. So by taking the length across any row and down any column, we can test this. And then we just need to check if this is composed of subsquares. So first we take the square root of a length of a side. Then we take the modulo of 1. And if this equals 0, it means the side length can form whole numbers when you take the square root. This can form subsquares. If it doesn't form a whole number, when you take the modulo of 1, it will have decimal values left over. And with those two simple checks, we can look for a valid shape. So once we confirm it has a valid shape, then all we need to do is confirm that the arrangement of numbers is also valid. And this means there can't be any duplicates in any row, column, or subsquare. So down a given column, there can't be a duplicate value. Across a row, there can't be a duplicate value. Or inside any of the cells in a subsquare, there can't be a duplicate value. So how can we track this? How can we check for duplicates within any of these given arrangements? Well, a brute force way to do it would be to iterate through, and then when you find a value, iterate up and down its column, across its rows, and then check all the values inside of its subsquare. This is brute force, and the time complexity would be very bad. So instead, what if we track the values? What if when we saw a value, we stored it in a data structure, and then we could reference this data structure anytime we encountered a new value to confirm that we haven't seen it yet. So to improve our time complexity, we're going to want constant time lookups. And the best way to do this would be hash tables. Or more specifically, we're going to create a hash table for every row and every column, and then based on the cell we're in, or the indexes of that cell, we can very quickly check if we've seen this number before. We're also going to use hash tables for the subsquares, but this is two-dimensional data that we need to track. Rows and columns are one-dimensional. It's going to be much more intuitive and just based off the indexes. And then we're going to work through and see how we can also use these indexes to track subsquares. So to track duplicates in rows and columns, we're going to use k hash tables. Or for a standard Sudoku board, 9 total hash tables for all the rows, and then an additional 9 hash tables for all the columns. And we're going to store these hash tables in arrays. So that's an array of 9 hash tables for rows, and an array of 9 hash tables for columns. Then when you're iterating through the matrix, let's say you land at the spot 2, 4. For the rows, you go to the hash table at the second index, and you check if the number in the cell has been seen yet. Then you also check the index for the column. You check the hash table at index 4, and also check if you've seen it in that column. So we can simply look for duplicates in rows and columns based on the index that you're at in the matrix. And then we just check the hash table to see if that item is a duplicate. So when we say we're using arrays of hash tables, it's going to look something like this, where you have an array, and then you're going to have k hash tables inside of it. We're going to have one for both rows and columns. And then as you iterate through the input matrix, anytime you encounter a cell with a number in it, you get the row index and the column index from the matrix, and then you access that index in this array. So the array index corresponds to a matrix index. And then the numbers you find in cells are going to be the keys of the hash table. And then the value for the hash table, we track the number of times that we've seen this number in this given row, column, or subsquare. So every time we see a number, we increment it by 1, and then each additional time we see it, we just continue to increment it. So the first time we saw the number 1 in this row, we initialize it to 0, and then increment it to 1, signifying it's the first time that we've seen this number. Then we did the same for 4, initialized it to 0, and incremented to 1. Then we did this with 7, initialized to 0, incremented to 1. But then as we were iterating through, we saw 7 again. So then we incremented this number from 1 to 2. Anytime we see the count has gone over 1, we know it's not valid. This means there's a duplicate in either the row, column, or subsquare. And when we have a duplicate that's indicated by a number greater than 1, we know the Sudoku board is not valid, and then we can return false immediately. So for rows and columns, it's pretty easy. We just have a one-dimensional array, and the hash table you access is based at the index that you're at in the matrix. But the subsquares are a little more complicated. They can span multiple rows and multiple columns. So it's going to require 2 dimensions to track this, and we can't simply access an array by its index. So let's look at some possibilities to gain some intuition. If you're at point 0, 0, you're in the 0 subsquare. If you're at point 1, 4, you're in the 1 subsquare. If you're at point 5, 6, you're in the 5 subsquare. So we can actually track this using another matrix, a matrix for subsquares. And we know this subsquare spans j values. So what we do is divide the index by j and then round down. So then anything 0 through 2 in a standard Sudoku board would round down to this 0 subsquare. But then if we look at 5, 6, 5 divided by 3 rounding down is 1. 6 divided by 3 rounding down is 2. So if we look at this matrix, that's 1, 2. So we can track these indexes of the subsquare matrix based on the size of the board. We simply divide by j, which is the side length of a subsquare, and then round down. And with this, we can always arrive in the correct subsquare hash table, and then we just track the numbers we've seen in the exact same way. And that's all we need to do to check for a valid Sudoku board. Let's quickly walk through all the steps to this solution. First, we'll check that the board exists so that we're even given this matrix. Then we check that the board is square by comparing the rows and columns. And then we check that it's composed of subsquares, which means we take the square root of a side length and then take the modulo of 1 to confirm it's a whole number. We're going to initialize an array of hash tables for our rows and columns, and it's going to contain k hash tables. Then we'll create a matrix of hash tables to track the subsquares. It will be j by j, where j is the square root of k. Then we start iterating through all n items. We start at 0, 0, and we go to the final row and column. Then, anytime we encounter a number, we're going to check the row and column arrays, where we track the hash tables for the numbers we've seen, and that matrix where we track the subsquares. And then we can simply use the indexes for the cell of the matrix item that we're at, and we can check the correct row, column, and subsquare this way. If it is a duplicate, we return false, or if it's the first time we've seen it, we add this item to the row, column, and subsquare hash table to track it. If we reach the final item in the matrix, and there weren't any duplicates, then at this point, we know it's valid and we can return true. So this is going to take O of n time and O of n space. We must iterate through all n cells for linear time, and for the space, we're creating 3 arrays, or really 2 arrays and 1 matrix, and we're storing k hash tables in each of these. Each hash table can contain k values, which is k squared space, or 3 times k squared space, but then we drop the constant, and k squared is n. However, one interesting thing I want to note about this problem is if we only used a standard Sudoku board, the space and time would be constant. Remember that big O is all about how an input scales. Well, if we're only using a standard Sudoku board, it's never going to scale. It's always 9 by 9. But in our case, it can grow arbitrarily large, which means we do need to consider any size of n. Which is why in our case, it's O of n, but if it was only a standard board, it would be constant. And now we're ready to write our solution function isValidSudokuBoard. And we saw to solve this, the two key components are checking for a valid shape, and then using a bunch of hash tables to just track values that we've already seen for the rows, columns, and subsquares. And to track those hash tables, I've already gone ahead and initialized some helper functions. This just creates an array of hash tables, and we pass in a size. And then for our matrix of hash tables for the subsquares, this just creates nested hash tables. So as we said, the two things we need to do are check for shape and check for the numbers. So what we'll do is write two helper functions to handle both of those cases. First, we check for valid shape. If it's not a valid shape, we can return false and don't have to worry about the valid cells. If we do have a valid shape, then we skip by this, and then all we need to check is if it has valid cells. This function will return true or false, so we just return that as our solution. Let's first write the function to check the shape. First, we just check if we have a valid matrix. We confirm we have rows and columns. If we don't, we already know we can return false. Next, we'll check if the board is square. We know it's square if the row length and the column length are equal. The sides are equal lengths. If it's not square, we can return false. If it is a square, then next we need to check for the subsquares. We take the side length, take the modulo of 1, and confirm it's a whole number. If it's equal to 0, it is a whole number, and if it's not equal to 0, there will be values past the decimal place left over. If it can't form subsquares, we return false. And if all these pass, we can return true. If we reach this point, we know it must be a valid shape. Now we'll check the numbers of the board or the content of the cells and make sure there aren't duplicates. Since we're validating the shape before we validate the cells, we know all these values will be correct. So we get the size of the board, or the size of one of the sides, and then we take the square root of that side to get the length of the side of a subsquare. So we initialize an array of hash tables for the rows and columns. This is how we're going to track duplicate values. And now we create a matrix of hash tables to track the subsquares. The length of the array for the rows and columns is going to be the length of one of the sides of the board. The matrix to track the subsquares is going to be j by j for k total subsquares, but it's going to be formed in a matrix. So we're tracking the same number of hash tables. Rows and columns are just linear, and the subsquare is two-dimensional. Now we just iterate through all the cells in the board. We use nested loops to go through all the cells for each row and column index combination. First, we just check if there is a number in the cell. If it's 0, the cell is empty, or if it's greater than 0, it means this cell contains a value. So if we do have a value, first we're going to check which subsquare we're in. And we know subsquares track multiple rows and columns, so we divide the row and column by the size of the subsquare to get in the correct one in the larger square. And then we round down, and this will get us in the correct slot in the subsquare tracking matrix. So now we want to track that we've seen a cell value for each row and column hash table. We're tracking this by incrementing it, so we're using a count. So we access the rows by the row index, and that gives us the hash table, and then for the hash table, we access the item for the cell value. So if a value already exists, we're going to use that. And if it doesn't, we're going to initialize it to 0. Then we add 1 to it. So we're adding 1 to either what was already there, or 0 if an item didn't exist there yet. And we do the same for the columns. We access the columns array where we're tracking at the current column index. This gives us the hash table, and then we access the hash table at the same cell value. Then we increment it, and if the value existed, we use that value, or if not, we default to 0. And now we need to track it in the subsquare. The way we track subsquares is in a matrix. So we access this matrix by row and column, and this returns a hash table. And then we access this table at the number from the cell. We again either use the number that was previously there, or 0 if it didn't exist, and increment it by 1. When we increment by 1, this is just indicating that we've seen this number again. And if it's the first time, it will just be 0 plus 1, or if a value existed, it's that number plus 1. And finally, we want to check if there are duplicates. We know there are duplicates when the count is greater than 1. If the count is only 1 for this value, it means it's the first time we've seen it in any row, column, or subsquare. If any of these show as a duplicate, the board is invalid and we can return immediately as false. If we iterate through all these items and we never return false, then that means the board is valid and we can return true. We run our code and the tests pass. So we successfully checked if the initial state of this Sudoku board is valid, and we did so by checking the shape of the board and then used hash tables to track if the numbers in the cells are valid. Thanks everyone, and I'll see you in the next lesson.